Okay, great. So we are live. Thanks everyone for tuning in. This is a live science session where we're going to be discussing Bohmian mechanics. And we are joined by Mads today and Nick. So I thought maybe it would be a good idea just to touch base quickly on what Bohmian mechanics is. I know quite a few people were kind of quite interested in this, and it feels like the forgotten sort of uh, idea that like an alternative view on how to do quantum, and so a lot of people have a strong feeling that this is like kind of a nice way to do it, or preference for one or the other. So it's interesting, and yeah, I'm looking forward to the chat today. So Mads, can you tell us what is Bohmian mechanics?
Thanks, guys, for the invitation. Let's see. Maybe we start with a very quick history of quantum theory. One of the most innovative ideas, at the beginning of first quantum revolution was de Broglie idea of massive particle having a wavelength. Okay, so basically, it's been shown and it's been observed that for example, light can behave as a wave, also as a particle, and then his innovative idea was okay, what if also the massive particles is the mass, they can behave like a wave. And actually that was the main motivation for Schrödinger to write down his famous Schrödinger equation, wave equation, because he thought he's describing a real wave propagating in space and time. Anyhow, it turned out no, that's not a real wave, and then the whole story of foundation of quantum theory, what is the meaning of wave function, what is truly describing, then Bohm rule, etc., etc. So fast forward, one of the leading scientists, one of those big towers of both mathematics, computer science, and foundation of physics, von Neumann. He wrote a very famous book on clarifying the mathematical foundation of quantum theory. And there, he clarifies what we usually define, describe as a no-go theorem, that something is impossible, you cannot do something. And one of that was the whole idea of kind of hidden variable theory, how you can better describe quantum theory by adding more variables. We call them hidden because they are not included in the normal, in a conventional description of quantum theory. But anyhow, it turned out one of the subtle assumption in his argument was wrong. It was pointed out by it was clarified by the famous John Stuart Bell, the famous Bell theorem, Bell inequality, and and in fact David Bohm, he wrote basically an alternative theory, a hidden variable theory, reproducing all the quantum result, but removing all those ambiguity around quantum. Of course, because of the Bell theorem, we know that there is always a price. When you go toward describing nature in a more deterministic way, providing a bare picture of nature, there is a price you have to pay, and that price is basically non-locality, which is the main consequence of Bell theorem. But anyhow, long story short, what we usually call as Bohmian mechanic or de Broglie-Bohm theory, it has an alternative name called pilot wave theory. And I think that name describes the pilot wave. It's mostly because the wave function, it acts like it's steering the particle in a space, and now the hidden variable is going to be the position of the particle. So really the particle, each individual particle, they have a well-defined position, and the trajectory of that particle follows a dynamical equation. And with some initial assumptions, such as if you assume at the given time, the distribution of that position follows the modulus square of the wave function, you can easily show that at any future time, it follows the same distribution. That's how you recover Bohm rule. One interesting question at the foundation of Bohmian mechanic that also got the interest of John Bell was what about let's call them the discrete degrees of freedom or internal degrees of freedom, how you would describe them in a sense with the same picture. And of course, there is another fundamental question, is still one of the open questions at the foundation of quantum, how you can let's use the word following a very positivistic approach, falsify these theories. Is there any experimental scenario that you can distinguish between the prediction of quantum and Bohmian mechanic. But today, I think we are trying to kind of tackle the other question, what about those degrees of freedom that we usually describe in the Hilbert space, and how we can add Bohmian flavor into that.
Yes, exactly. So that's, I guess that's the plan here. So I have your notebook, Matt. So
that notebook goes ages ago. It's when was 2018? Yeah.
But I think it serves as a good introduction, like a computation introduction into Bohmian mechanics. So this is was it your summer school project? Right?
It was a computational essay that I did, during the summer school 2018, and that was basically my main reason that I decided to leave academia and join Wolfram Research. We are gonna blame the guy who helped me a lot, with this, computational essay was Paul Abbott, one of the basically the veteran of summer school, and he's also coming this year to the summer school. So thanks to Paul for guiding me through this project.
Very cool.
Yeah. So this is essentially an essay that describes a two-slit experiment, right? A double slit experiment, by actually computing all the pilot wave trajectories, the evolution of the pilot wave itself, and just showing it the nice pictures of what actually is going on, right? And actually the actual values of the distance between the slits, all the values, even the speed of light are all explicit here. Even the Planck's constant, so it's very down to earth physics, not in some arbitrary units.
Right? And by the way, that's a real experiment, done by Anton Zeilinger, the famous physicist who got the Nobel Prize 2-3 years ago. So those experimental data, it's a real experiment that's been done.
Very cool.
Yeah. So this is this is the picture, for example, is an evolution of those two pilot waves emanating from two of the slits, right?
Oh.
Right.
So does that vary with time?
Yeah, it's this is the slider for the time. That's how they collide and interfere with each other. It's maybe just showing the probabilities would be clearer. Right? Nice. The black one is the sum of them. It is the sum of them.
So basically, the way that we can think, if people look at the top picture, that's two wave packets. You see, the coloring that that are there, the red one is the one to the left, the green one to the right, and they are moving toward. Of course, they are coming through the slit, but you can just consider the direction that you have your double slit, and they're coming together, overlap, and then they again colliding, and then they go separate waves.
Yeah, here I think the picture is basically the screen is in the middle, right? If there wasn't a screen, they just go through each other.
Yep.
So the only interference is in the middle.
Yes, and basically if people see that the cross section of that density plot is that interference pattern that Nick showed you on the top.
Yeah, so this is imagine that there's a screen here exactly in the middle. So this is the interference pattern that you see, or as a cross section is the black line there. That's the density of photons you'll see there, density of light. Now there's a 3D version of it, which is also kind of very visual, like this. And because of the Bohmian, right? This was just the evolution of the pilot wave itself. But we believe that from the Bohmian perspective, there are actually some definite trajectories of each of the particles. And depending on where the initial position of the particle was, it would follow some definite trajectory under the guidance of the pilot wave. And this is just some sample of those trajectories. Given that you start from the right slit or the left slit, that's how it would fall. And you'll see the same interference pattern because there is no trajectory going through some of the position, right? So here, none of the paths hit here. So that would be the exact result of the experiment here.
Basically, the only, the assumption, you see, that's literally the interference pattern that we observe on the top. The only assumption, as Nick mentioned, is that initial sampling. So when you sample, basically, this is a trivial case. It's not important. When at the very bottom, like, that's your initial position. When you do the sampling, you would assume that, like, that sampling follows, like, the modulus square of the wave function at your initial time 0, and then you just let the particle evolves. Like, of course, like, there are some, subtleties in Bohmian mechanic. For example, like, many other, practically any observable in Bohmian mechanic, we use the term contextual, meaning, for example, like, look at that middle that we have the interference pattern. As you see, like, more or less all the, like, the pathways are kind of straight. So people would say, oh, okay, if it's straight, then, like, majority of particles at that position, like, their velocity is kind of like, the same, like, all of them, they have the same velocity. When we say contextual, that's the whole story of Bohmian mechanics. So it means now, if you think about any other observable, the context, let's say the measurement apparatus and the way that you design that, is going to changes everything. So you cannot say, oh, because of, like, all of them are kind of like, a straight line, then, like, this is going to be the velocity that I'm going to observe in experiment. And it would say, oh, it's as if, like, I'm contradicting, like, for example, Heisenberg, uncertainty principle. That's not the case. So if you want to observe the momentum, it's going to be a different experiment, a different trajectory. Everything is going to be different. So that's the meaning of contextuality, like, in Bohmian mechanic.
Yeah. Well, my understanding is that all that is definite in the classical Bohmian perspective is the position of the particle and nothing else. Every other property of the particle, like spin, momentum, energy, all of those properties are essentially contextual because of the pilot wave. So it's not just some property of the particle itself, it's also only valid to ask those properties in relation to the pilot wave too. So right. And only the position is definite. Yeah. And that perspective I actually want to change today a little bit, because just for the sake of it, it's not bad to just consider this kind of idea. What if it's not, right? What if, for example, a spin of the particle was also explained in the same exact procedure as the position of the particle in the Bohmian mechanics, but for the quantum computation case, when you just have a discrete value instead of continuous position, how you can explain this property using the same kind of ideas and a definite property evolving together with the pilot wave, guiding that property, right? And what I have here, another notebook, right? Now we go from the quantum mechanics, when we have particles with their positions continuously evolving in space. Now we have just a simple quantum computation picture, right? So consider my example will be just on a single qubit for now, right? So, and the most simple example that you can imagine is that if you start with some definite spin up, which we usually in the quantum computation describe as a spin state 0, if you just rotate it by some angle, right? So that's our evolution, just the simplest possible example you can imagine, right? If you start, hold on.
Can we zoom in maybe 150 or so?
Yes.
Okay.
Let me load the packet first. Okay. 150. Okay. Okay. So we have this circuit. So that's our final probability. So if you evolve this definite spin up state by rotating it by pi over 3 degrees, that's our final probabilities of measuring the qubit in either state 0 or state 1. Right? That's what we want to represent using Bohmian computation, I guess we have to call it right now. So in Bohmian, so we want to reproduce this picture in Bohmian style. So if our initial state is 0 and our unitary operation is this rotation by pi over 3 degrees, we should represent it continuously because usually computation is described in this digital fashion when you have just a single unitary gate that you apply one time. So it's like just single step, your state immediately jumps to another state, right? So that's not how Bohmian thinks about this kind of evolution. So we have to go into Hamiltonian picture. So essentially just take the logarithm of your unitary evolution to make a Hamiltonian, so that essentially if you evolve to your initial state by like you basically solve your usual Schrodinger equation with the initial state in your Hamiltonian, you'll get the same kind of final state as just applying the unitary. So or you can just see what it does depending on the time, how the state changes when you evolve it from the initial state for some single unit of time up to 1 unit of time, right? So that's just our power-free rotation of our initial state. So that's our continuous evolution. That's how the actual amplitudes change. They actually, in this simple example, they're all real. This is how amplitudes of 0 state changes 1 and their probabilities. And if you want to actually think of it as a pilot wave of sorts in a discrete fashion, you should actually, in this computational context, you should think of it as this transition graph between those states. So what would so the analog of that picture that we had right here, right, where the pilot wave changing with time would be that picture where your transition probabilities from state to state changes, or transition probability, something like that.
Is this our quantum flux?
Yeah, that's our flux capacitor. That's what we called it. So it's a like changing flux capacitor. That's our pilot wave changing in time.
So I think like, it helps if, somebody would say like, okay, those transition rates, how they are related to usual quantum probabilities. Maybe it helps if you just
it's a little bit trickier. That took some time for me to figure out, because what we usually showed here, those numbers, those labels on edges, they actually not directly related to the actual flow of probability, right? So in actually to compute the current of probability through the states, you actually have to do something like this. Is, for example, the original Bohm paper, when he considered this Bohmian mechanics for discrete systems, but not systems like spin, but some kind of lattice instead. So instead of just having a continuous position, he just considered some discrete positions. And he had this notion of the transition probabilities. And if you basically, what would be the probability of jumping from one state to another discrete state would be proportional to the actual time interval and some transition probability, right? That's how, and how it is computed. It's computed from this current, which depends on how your state evolves. Here's the Hamiltonian, the final, and your initial and final states, and the actual probability at this position of time of the pilot wave. So all of these quantities can be computed from the pilot wave. This is the same thing for more modern paper I found. This is the same kind of current that you have to compute from given the pilot wave and how it evolves. You can compute the current from one state to another state, and that would be, and how you would compute the transition probability from one state to another at every single instance of time. You multiply this current by your interval of time and divide by probability. But you also restrict yourself. This is like the important part, which was also present here in the Bell paper, that if the current is negative, your actually jumping probability is 0, because its probability is not allowed to be negative. Yeah. So here, just to explain what this actual thing is and how you can compute it. You can think like of Hamiltonian is just having some off-diagonal terms, and in a way, that's tell you exactly these terms that you want to compute that relate the Hamiltonian to the current. So we want to compute essentially the expectation value of these off-diagonal terms. So if you turn, so your current from 1 to 0 relates to this term, and your current from 0 to 1 relates to this term. And the way you can do it is by computing these projectors, exactly that you see here, which you see here in the formula, from to 0 state and 1 state. So we have just 2 projectors. And in order to compute the current from 0 to 1, you just compute the expectation value, which is like this composition that you can compute, exactly like what it says here. The imaginary part of the diagonal term of Hamiltonian. And you can simplify it and compute this current from 0 to 1 and from 1 to 0. If you plot it, you'll see that the current for a state changing from 1 to 0 is actually negative. So there's actually a 0 probability of jumping from 0 to 1 in this case, which kind of makes sense if you look at the picture of how it evolves. If you're already in 1, you better stay there or something. Well, actually, your initial state was already 0, so it can't be 1, so it doesn't even make sense to consider it. But anyway, for this very simple example, you can determine the actual probability of at the end, at the final unit time, after 1 unit of time interval, what would be the probability of state of your particle. In this case, your single particle is just jumping around. You should think of it now stochastically instead of when in Bohmian mechanics, particles are continuous and evolve continuously with time after you solve some differential equation. Because of the nature of the discrete space now, your evolution has to be stochastic. So particle, instead of evolving continuously from one configuration to another configuration, it now stochastically jumps from one state to another. And this is the jumps that are allowed, right? So the only jump which is allowed in this case is from 0 to 1. And in order to compute the final probability, you just integrate this current. So basically this curve, and you get the probability of the particle being in one state, which is just a. Is it correct? Yes, that's the one. Where was what our final? Yeah, this is basically it's end up here. So this is the probability of 1/4 exactly. The probability, that's how our state evolves. The probabilities of states evolve. And if the particle were in the 0 state, that's the probability of it jumping to the 1 state. So that's everything is checks out, right? Do you have any questions? Because it's going to become a little bit more complicated.
Up to here, I think it's clear what's happening there. Basically, just to summarize, we are reproducing those formulas, in original Bell's paper on Bohmian mechanics.
Yeah, exactly. Yeah, we're producing this paper, these formulas, and interpreting them differently from Bell. We're now interpreting our discrete states rather than some lattice positions. We interpreted them as spin or just 0 and 1 states from quantum computation. And we can just represent it as definite value. So we think of the actual particle or qubit be in the having a definite value of spin up or 0 or 1 state. And it just stochastically can jump from one to another. In this case, it's just because we assume that it's always in the 0 state, because that's our initial probability. The only thing that can happen, it can jump from 0 to 1. And that's the probability of it jumping. And that's how we can simply compute the final probability. So that's how it works in the simplest example. But in general, right now I'm going to do the same kind of thing, but in general, so that we can reproduce the exact same probabilities when it's not, when the initial state is not just a single state, and it evolves again with the same Hamiltonian. But I don't think that matters too much. It's again the same kind of rotation, but from some other random position. This is now it's not just real amplitudes. Now our amplitudes are not just real; they actually have some complex imaginary component to it. So that's how the evolution of the wave that behaves here. So they both have real and imaginary components. So that's the evolution of the wave. You can compute the same kind of currents. You compute the same current, probability currents from 0 to 1 and from 1 to 0. Now they you don't have the same situation as before when one of them is completely negative. Sometimes one of them is positive, and another time another one is positive. I think it's in general the case that it's always one of them has to be negative. So there is always an intersection is somewhere with the axis, with the time axis. So you can compute the time when the flip happens, when the state is allowed to jump from one to another. That's
like at that point that transition happens. Where is it on the block sphere? Is it easy?
I think it's just when it starts to cross this great circle over here. I think that's where it is.
I see.
Yeah. So it crosses this guy. So it's not completely obvious why we do this case, because we're considering the axis of between 0 and 1. Right? Why would it matter on which side of this hemisphere we are in? Not completely obvious, because it's symmetric in relation to this axis. But that's what happens to the pilot wave. So if you want to, for example, to actually see the negative probabilities, the final transition probabilities, you integrate. Oh, I haven't regulated this, guys. If you integrate these currents, you actually see that one of them is negative. So in the conventional computational case, if you in not Bohmian case, if you want to compute the probabilities, you actually use this negative probability in order to compute the final one. So this is the probabilities that we want to reproduce. The probabilities at 1 unit step of time. That's the probabilities you want to introduce. But you have to use the negative probabilities that you encounter when you integrate the whole current. Right? It's like you can't have this nice interpretation of this probability as some jumping probability. So that's what you have to do. But in order to fix it, you compute these values that always positive, which are those transition rates from the Bell paper, from 0 to 1 and from 1 to 0, and you constrain them to the positive only to the positive values, but this ramp is just cuts off all the negative values. So that's how the transition probabilities now actually behave. So each value here shows you what would be the probability of jumping from 0 to 1 or from 1 to 0 at some tiny interval of time. So that's the curve in this case. And I don't know how to set up. It's like a mathematical task that I can't solve right now. I don't know how to solve it, but it seems very trivial. It's a pity that Karos is not here. He's our mathematician. But I know how to just simulate it instead of constructing some kind of integral. You can just actually compute the finite discrete intervals. So that's my tiny interval that I'm considering right here. I'm just splitting it and computing at each point. This is like a giant number of how much. There's like a million number of probabilities. So just discretize the whole interval, and I'm considering the probability at each tiny interval. At each tiny interval, this 1 million interval. And in order to compute the actual final probability or the jump, here I just want to compute a probability of a single jump happening in the interval between 0 and 1. This is that's what was tricky a little bit. So you have to, for example, let's make as an example, let's make a smaller interval so that you can actually see. For example, like this vector, this would be the probability of jumping between from 0 to 1 in the interval between 0 and 1.1. This would be the probability of jumping in this interval, and so on. But then actually to compute the probability of jumping once across the whole interval, across whole unit interval, you have to compute it like this. For example, you have to consider this whole product, basically, in order to compute the probability of jumping once, you have to consider if it jumped in this first interval, it's either jumped in this first interval, so you have to sum up this number. Then you should consider, okay, or, that means or it's jumped in this interval, but not jumped in this one. So they have to be multiplied by this. Then you ask again, maybe it jumped in this interval, but it is not allowed to jump in either of those. So you compute it like this, and so on. So that's the algorithm for computing a complete probability of jumping. And that's how it is expressed in formula or in this finite computational, from this final computational vector, you can compute it like this. And that would compute a single probability, a single jump probability from one state to another. And in order to reproduce the final probabilities, again, like in this case, these ones, from these probabilities of jumping, you also need to consider what was the initial conditions. And it was, in this case, it is easier to just consider the jumping, the probability of being in one. It's much easier. For example, in order to compute the probability of being in one, you can kind of, from this picture, you can guess that it's either it was already in one. P1 in this case is just initial probabilities. So P1 and P0 are probabilities being. This is our initial probabilities. See? So in order to compute the probability of being in one at the end, it's either was already in one and it didn't, right? So this is the probability of it not jumping from 0 to 1, or it was in 0 and it jumped and then it didn't jump back. It stayed there. So that's how you can and that's how you recover the probability of it, this probability of the final probability of it being at state 1. Probability of being in 0 is actually a little bit trickier, but as an exercise, it's still, I think, important to consider, because there you have essentially 3 cases. For example, in order to compute the probability of it being at 0, it's either started at 0 and didn't jump, right? It stayed there, or it started at 1 and jumped, or it started at 0, jumped to 1, and then jumped back. So that's kind of 3 cases, because in this case, when you started at 0, you could have jumped here and also jumped here. So that's what for 0 it was a little bit trickier, and you recover the same kind of number here, the probability of 0. So that's how it works. So it's a stochastic evolution. I want to figure out what is left to figure out here is just how it works in the integral equation or something. I want to be able to set up an actual continuous integral and solve it here, and actually to reproduce these probabilities for the simple example. But in general, that's how it works. Your particle not just jumping around. It can either jump once, sometimes it can even jump twice. But the actual final probabilities exactly recover the probabilities from quantum computation, and we can change the Hamiltonian. Nothing here is limited in a way we set it up, so it's pretty general. We can change the Hamiltonian, our initial state, and even the dimension of our system, and reproduce the exact same thing. Maybe it's a little bit trickier when the jumps are between not 2 states and 3 states, but in general, that's how it works. So I think that's all I have here. I for a day, so I did consider how it should behave itself in phase space, but it's a bit tricky because I was confused how the particle can be in definite state of spin up and spin down, even though you can measure it in some different direction. So that particular thing was clear for me, but then I kind of understood, but it's not even the case in the usual Bohmian mechanics, because there the position of the particle is also depends on the reference frame. So here it's essentially the same kind of thing, but instead of thinking about that you can change the reference frame and your representation of the position and coordinates would change, you essentially would change the measurement outcome. So in this sense, your measurement setup is like your reference frame. So depending on how you measure, you see the particle in a different flavor. So here we just consider that we will just fix the reference frame and looking at a single direction, where like spin up, spin down direction, for example. But you could have just changed it, and that basically would change the coordinate position. The only problem that you wouldn't be able to recover it from the probabilities in general, I think. Right? If you are given the final probabilities of measuring spin up, spin down, that wouldn't tell you exactly what were the probabilities of it being measured in other orientation. That because of complementarity problems, you have to like solve the same kind of problem, but for different coordinate reference frame. In this case, coordinate is just a rotation of the spin, but that still would recover the same kind of results. That's it. So maybe you have some questions.
So like, I think like, one interesting feature, I don't know, like, if we can provide that visualization easily, practically, like, let me try to rephrase, like, what's the difference between this picture and the usual quantum evolution. So the usual quantum evolution, you have a continuous trajectory basically in the Bloch sphere, and that's basically how it goes from one point to another point. Yeah. What here we have is basically very similar to quantum jump stochastic dynamic. Like, it reminds me of like, those, the stochastic jump dynamical equation that are out there. And one wonders, like, would it be possible, for example, for the timeline of like, 0 to 1 look at a very specific trajectory, like, like at every increment, if it jumps happens, it goes to the other one, and then like, so like a step line function, and that step line function is either like at the bottom or at the top. Like, do you think it's possible to have a plot like that?
Yeah, but it's just in this case, the jump only happens maximal twice. Right? For in this case, and it's always going to be the case, I think, for a qubit. It's either jumps here and jumps here, or just jumps here. So it's not just jumping around between them. As soon as it jumps, it's there's no, the probability current pushes it and fixes it in this position, in this state, and doesn't allow it to jump. Unless like after some time it evolves and actually provides some opposite current, and now it can jump. So it's not like it's jumping around, it's just a single jump. So I'm not sure how do you visualize it. It just happens randomly somewhere. We can visualize it by some kind of sampling a bunch of particles, essentially, right? That just jumped at different times, and then we can compute it just as statistics. We can recover the same probabilities by simulating different particles. Yes.
And that jump probability formula that you have there, like, the first, let me apologize for my lack of like, mathematical details. That delta T that you had down there, it was already.
No, this
so, yeah. So that, if treating that as a dynamical equation, it's look like a dynamical equation that you go up to the order of second order in delta T. Right? Like, that's, you see, we have a delta T there, we have that delta T there, and
but it's not even a second product, because it's like this is a product, and essentially this.
Oh, you're right, even higher. You're right. That's a product. Yeah.
Yes.
You're right. In my mind, like, I saw that as a summation. It's not a summation, it's a product. Yeah, one wonders, like, what would be the And what's going to happen, like, Nick, like, the visualization on the top that provides, a clear picture of jump. What if instead of like, that Hamiltonian, basically put a random Hamiltonian, like, of course, a fixed random, like, here you just have a Pauli Y rotation.
Mhm. Let's do this. Let's fix it. Yeah. Let's evolve it. And it. That's a different Hamilton. Maybe I should have done it here. It's me. When I was already considering this.
Mm-hmm.
So instead of just simple rotation, I'm doing some larger rotation essentially.
Mm-hmm.
See, that's evolution, different currents. Oh, that's
Okay. Yeah. That was the thing I wanted to see. So there are more than one crossing.
yeah, I guess that's possible because that's always going to be some sine and cosine curve.
Mm-hmm. Mm-hmm.
But we can change the frequency. It can even be more, right?
Mm-hmm.
It essentially depends on the frequency. If our Hamiltonian was instead, again, this log of, is it basically a very small angle? It's a very small angle. What would it be? Right, so I
A
guess,
very large angle.
yeah, the angle doesn't correspond to this. Yeah, well, it's maximum 2 pi, so it actually has a constraint. So it's just a sine of cosine curve, which is flat.
Mm-hmm. Mm-hmm.
You can see. Oh, 2 pi is just
Yeah.
Let's try random again. Let's just look at this example completely. What happens with these two crossings? Oh, look at this.
Oh, yeah, look at that. Yeah.
That was a nice. Okay, so a high frequency Hamiltonian. This is.
And then, one other thing that one wonders is like, what would be the connection of like, those negative transition probabilities and the transition graph that we have based on phase space? Are there completely different animal, or are there similarities between them?
What are you asking? The phase space.
So basically, like, if you scroll up, like, see those transition probabilities, that there is a possibility of negativity there, transition probability that we have there.
Oh, that's a current.
The lower one, after doing the integration over time. It was immediately before that graph. Yep.
Well, this one.
Yes.
Well, yes, because we're integrating this curves.
Yeah. So I wonder, like, that one, does it have any correspondence with the transitions that we have in the phase space, like, that graph that you showed on the top, or it's just a completely different thing?
Maybe. From the phase space perspective, I was kind of wondering, maybe we should consider, instead of 4 different states, let me briefly show you what I have here. I was considering kind of the same kind of thing there. It was even before when I understood how the current works. So I was kind of didn't work. Nothing worked here. But I was considering that instead of 2 possible outcomes, like spin up, spin down, 1, 0, you should consider 4 of them. All those phase space, like these guys. For example, in the Wooters, you can even label them like this. That's, you basically evolve your pilot wave now controls 4 discrete states, and they evolve in time. I was kind of also consider how would measurement work. It's like in this particular basis, it's very nice. It just combines 2 of them, and that would be the final probabilities. But I guess you can do the exact same thing there. It's just I'm not sure how. Yeah, your formula for current would be different. It's not really, it doesn't have to be, there's nothing imaginary there. You don't have a Hamiltonian, you just have a quasi-stochastic evolution in a way. So yeah, I'll try to figure out how it works in the phase space picture. Presumably it would be even simpler. But in the end, you basically have not a particle jumping around between two states, but the particle jumping around between four states. And that, but then at the end, some states got equivalence when you measure them, for example, like depending on which basis you choose. So in a way, it's more natural because it's still a bit weird to consider that there are different bases of measurement would change what your particle is, where it kind of changes the nature of the particle. But from here, it doesn't change its nature. It's just you just start in equivalence in them, so it's a bit more natural. But I think the same kind of analysis with the current and transition probabilities and stochastic evolution between states would still be applicable here. It's just the formula would be different for the current and all that. Yes, that's the next thing to figure out.
We have a couple of questions in chat. Should we take some of those now?
Sure. Yeah.
Okay. Cool. So Petrol Science was quite interested in this Bohmian mechanics interpretation, specifically related to some of the stuff he's doing. The question here is: in ER equals EPR, entangled particles are connected by a wormhole, but both mouth need not be at the same coordinate time. Could this feature of entanglement be required for a Bohmian mechanics interpretation of quantum computation? Then he goes on to say wormholes allow non-locality to be constrained to connections between distant particles, whilst allowing the nearby fields to be otherwise local.
Well, first of all, original Bohmian mechanics wasn't relativistic, so it's just like a single coordinate evolving in time. But the problem was there, or in order to resolve all the relativistic non-local debates and all that, it's just the important thing would be there to understand is that your evolution is not of the particles but an actual configuration space. That's where your pilot wave is described. The pilot wave evolves in the configuration space. Essentially, it's just all the positions of the particles forming this one single space, and that's where the evolution is described. And even the particles themselves kind of evolve also in the configuration space. The fact that they are correlated there, and when we actually look at the projection of the configuration space and the positions of each individual particle, that's where I'm not sure how to explain it. It's just different kind of thing that we're observing to the thing that is actually evolving. That is like we actually have some substrate. In the physics project, actually, we have a nice interpretation of the configuration space, because in configuration space in physics project would be an evolving hypergraph. And the actual positions of particles or any other kind of property is emergent from there, or if you think of it as a projection from this configuration space to some effect that one observes looking at some events of rewriting the configuration space. So that's the interpretation there. But the only common point is that there are two different spaces, and it's not clear how to marry them together and how to describe them, because I'm not sure personally.
Is there an experiment that would differ in the Bohmian mechanics interpretation to quantum field theory? So is there some experiment that you could say, okay, well, something like Bohmian mechanics is a more accurate way to describe what's happening with some experiment? Or is every experiment you do with QFT going to give you the same outcomes here?
Well, in QFT is a little bit more problematic. Quantum mechanics should be equivalent. It's very easy to show. quantum QFT is exactly what was the subject of these papers, maybe indirectly, because if you consider your discrete evolution, or instead of you considering positions as some continuous variables, you consider some discrete variables. I think instead of actually having, if you consider some lattice and your variable is some population number of fermions or something like that, you're essentially doing QFT. So if you describe your configuration space as number of fermions sitting at each node of the lattice, and you consider evolving that using Bohmian mechanics, that's the idea is that would produce the QFT picture. You're doing the second quantization, and your discrete variables is population number of fermions. Yes. Good. Well, I don't know how it works. I'm still learning.
So there was one criticism on Bohmian mechanics which said that where the particle is in these kind of waves, I'm just thinking of it purely visually, what happens is, like, if there's an observation or there's some kind of probability that the particle is in one of these troughs, more probabilistically, the other probabilities don't disappear. Like, it doesn't completely collapse. There's still this potential for the particle to show up somewhere else. And I might be paraphrasing, but potentially there in experimentation you'd see particles like jump like all of a sudden non-locally to other locations.
Particles never jump.
Okay.
The Bohmian particles,
Yeah.
well, in the usual mechanical sense, the position doesn't jump. So like even if there's a wormhole or whatever, I think if you describe an entanglement as a wormhole, what you're essentially describing two particles at two different sides of that wormhole evolving.
Interesting. Okay.
So because it's an entangled pair, we have so it's not a single particle sharing a block hole, the wormhole that can jump like between its ends. It's actually two particles that share a correlation between them using the wormhole. That's what entanglement actually in this ER equals EPR conjecture is, right? That's not a single particle. So you're evolving two particles and they follow the definite trajectory in this Bohmian picture, and the wave still, even the wave that is not jumping, the wave also evolves with the speed of light. There's no jumping. It's just it guides to those two particles, and their correlation also starts to be apparent because the single wave influences both of them even through the wormhole, whatever. Maybe this effect that this evolution through the wormhole can happen, and the wave can essentially guide them effectively as though there's a shorter distance between them or something like that.
Okay, we have another question here. How are you measuring the system? Or are you just measuring the probabilities of the structure?
In what case? In this case, measurement is very straightforward because we have a definite particles, a definite state of the particle, spin up, spin down. So every time we just do whatever particle is at the end of the interval, that's what we observe. So there's no problem at all here.
Wait, why does that end the orange line at about 0.8 or so? Does it jump down to the bottom?
Yeah, well, that's a very interesting case. It's just, yes, basically here it starts, again, we have three different transitions. Now, in this case, the way I computed probability with only a single intersection, it's not gonna do it. Now a particle can jump 3 times. So I guess we need a better way of computing the final probability from this perspective. In general, even for a single qubit, there can be arbitrary number of jumps.
Okay, then just to follow up on the wormhole idea there, and a wormhole can allow them to shuffle quantities, like spin between them. That's just a comment.
To shuffle Oh yes, if we're gonna treat spin like we were treating this 0-1 states here, stochastically, it's just the pilot wave only controls the probability of jumping from spin up, spin down, and the pilot wave evolving with the between entangled pairs. I want to show this more explicitly maybe in the future when we have two particles, not a single, two qubits, not a single one, how that would work. But essentially, your pilot wave would control the transition probabilities of two of those particles and spins between them in correlation. So there's some kind of correlation between them, would be not of the jumping probabilities from one state to another.
Okay. Interesting.
But but they still jump in a way independently of each other. They not the particle itself don't influence another particle on the other side. It's just the wave controls probabilities in this correlated fashion.
Yeah, that'll be interesting to see that version. So I had a few questions, Mads, around the narrative of these things. So why do you think it is the case that the Bohmian mechanics interpretation or this theory was so attacked by the scientists of the time? What do you think it was about it that seemed to attract these negative comments at the time? And do you think there's some kind of comeback in terms of having this alternative? Like, is there some kind of advantages that have become apparent or maybe more useful over time? Or is it just kind of interesting to have a alternative theory that sort of works out as well? Is it just useful?
I feel like it's not special about Bohmian mechanic or anything like that. You would see it in the course of history of science. Many of the Boltzmann original ideas, they were not that much acknowledged or appreciated when he basically shared that with the scientific community, right? Or even Maxwell's ideas on the statistical mechanic. It took a long amount of time for the scientists to come to a conclusion that what's really happening there. That goes the same with quantum. And I think there are many interesting books about the history of quantum and the whole dynamics of interaction between the founding fathers, very strong influence of Niels Bohr. And it's very funny, maybe many people, they know this piece of history that John Bell, when he was working on the foundation of quantum theory he was at CERN, and he was basically hiding all of those research from his colleagues because all those harsh criticism that he may face. And if you look at the journal that he published, that if I remember that correctly, that journal doesn't exist no more. Or when Alan Aspect went to Bell and asked him, "Oh, I want to do the experiment on this," he first asked him, "Do you have a secure job in academia? I don't want to ruin your future by you working on this thing." And then 40 years later, Alan Aspect got the Nobel Prize in physics for doing that experiment. So we have had lots of ups and downs in science, because those who do the scientists, they are humans, and everything regarding the nature of humans goes directly into the science that they do. Many people, they have this impression that it's very abstract, it's mathematical equations, and that's no, not at all. It's always human interaction is always how scientists are interact, who is friend of who is the leader, who has the resources, who has the money. But it's a very interesting piece of history. And not only that, there are more alternatives. There are many different ways of if I remember that correctly, there are 9 different formulations of quantum theory. And the most popular one is still Schrödinger equation and somehow the Dirac notations. But there are many others. You can do everything in the phasor space, with Wigner functionalities. But I don't think in any undergraduate school, I don't think students ever exposed to phasor space formulation of quantum theory.
Interesting. So why did those theories how do you win as a theory? In other words, is it the thing that makes most narrative sense sometimes? Is it the thing that's easier to teach students? Is it just a lack of history that it just ended up that way and we don't want to change?
Of course, like, if you ask different scientists, like, they would have different opinion on that. The narrative is a very important, like, effect, because we need to communicate. And when it comes to communication of ideas, you need a narrative. And funny enough, every people will say all narratives are wrong, right? For example, like, right now, quantum computing is one of the hot topics. Some people would call it, like, one of the buzzwords. And there are people who develop, I know many of them, amazing algorithms, like, using quantum theory, but they are not familiar with dynamical equation of quantum theory. They don't know what is, time evolution. They never touch, like, Hamiltonian or time evolution, which is basically the whole concept that, like, physicists or chemists, when they learn quantum, that's what they learn. So depending on application, depending on, like, what you would do, you would have a different narrative or different paradigm of, like, communicating, like, those ideas. Some of them are very, very abstract. Some of them are, like, more tangible. Like I can tell you many of the things that Nick is doing, like, in the conjunction of, like, physics project and quantum, I don't understand them. It's like way too abstract. So it's like, that's why, like, I cannot touch it, mostly because I don't understand that abstraction. So I again, emphasize the human factor. It plays a very, very important role. I can tell. Let me add, one funny thing about Wolfram Physics Project. One of the, I'm not gonna, mention his name, but he's a very famous, computer scientist who is also working on quantum computing, and he has this interview of, like, criticizing, Wolfram Physics Project. And if you watch that, in his mind, Wolfram Physics Project is the same as Cellular Automaton. And when I watched that interview, I was like, oh my gosh, like, it's not, like, calling, like, Wolfram Physics Project as, like, Cellular Automata. It is not that, like, but even some leading scientists, like, they have this misconception. I don't know, Nick, would you like to add, like, what are your thoughts on why, like, the Bohmian mechanic less popular? Or
Well, I'm not that familiar with history and why it happened. why scientists decided that Schrödinger picture is the prevalent and why it's won above, and why Bohm was shattered, and why de Broglie essentially stopped working on it. Yeah, I don't particularly understand the reason. It's just perhaps they thought that that's. I remember that what was the Einstein, I think, said that it's like a child play or something like that. Thinking about those particles evolving with time in the sitting on a pilot wave, which I'm not sure why, because it's if you think about it, maybe because it's the major development of the Bohmian mechanics was in the period when the field theory was developed, and maybe it's too childish to consider this mechanical picture of particles when there's actually was this idea of fields was more prevalent.
Yeah. By the way, like, Nick mentioned, I forgot to, like, this is a very sad piece of history about, like, Dubro himself. Like, the attack on him and his ideas was so harsh that for many, many years, many decades, he just didn't touch his original idea. And then it was rediscovered by, like, the David Bohm. Like, it's sad. So it's like he has started that, and then the attack of, let's call it, Copenhagen School of, like, quantum, and then he didn't work on that. History of science has many of these examples. It's not only quantum. In every field, like, you would see something like that.
I was interested in the last stream last week. We were thinking about the narratives, comparing Schrödinger's if you think about Schrödinger and the cat, right? Schrödinger's cat. It's a very visceral type, tangible thought experiment. You can think of a box. You can see a cat. You can maybe, like, picture your cat in the box. It's like so easy. And then we're trying to think of like what would be the equivalent narrative story for what is it, Nick? Was it the Heisenberg interpretation?
Matrix mechanics.
Yeah.
Essentially, yeah.
So like, what's the story that you can talk about with like physical objects to explain that interpretation? And we're struggling to form a narrative around it.
I guess it would involve a bunch of oscillators. Yeah, because that's exactly what I think the matrix was in the original Heisenberg interpretation. Is that instead of a particle or whatever it was, the system evolving, having a definite trajectory, it has many trajectories, and they were not. And you just write it in a matrix. Essentially, that's how it works. Yeah.
So I thought one way to describe it was you open the box and then you ask, is there a cat or not in the box? So you get like one type of answer to the question, but you're not asking whether it's dead or alive. Or you open the box and say, is what's in the box alive or dead? But you're not sure if it's a cat or not. So it depends on the observer's frame of reference or something. Would that be an accurate way to
So basically, like, if anything, like, if I may, foundation of, quantum theory, it's a very interesting topic, but of course, like, very difficult. Like, Dirac at the very beginning, or like, after making so much progress on quantum, he identified two types of like, problems, at the foundation of quantum. One was, field quantization, and the other one was foundational problems. And, he has this famous saying, he said, we are not ready yet to tackle the foundational problems because they are very difficult. Let's focus our energy and, training of the next generation to, toward, field quantization, which turned out to be a very successful, like, program.
Interesting.
But if anything, like, my recommendation for anybody who wants to learn these topics, read the original papers. Like, you will be surprised how different are original papers from even, this, we are talking about the history of like, narrative, even the narrative around Bell theorem, his original idea, his program, what he wanted to achieve, and the way that like, scientific community is now treating Bell theorem. I'm sure if he was alive, he would be so upset by the way that scientists are thinking about like, Bell theorem, because it's exactly the opposite of his original idea. Like, it's, for example, measurement problem, Schrödinger cat, Wigner friend, and many others. Like, these are different scenarios that in a very nice dramatic way, they kind of communicate the problem of measurement. And but at the end of the day, like, it's the same. Very recently, like, we were discussing with Nick, and one of our colleagues asked for some computational essay on Wigner friend, and we did that, and we were like, okay, so it's nice. It's it's a nice drama. Like, now a friend is involved. He's conscious. They're conscious of like, collapse of the wave function. But does it help to understand? Like, yes, as a storytelling is fun. Like, it's like the whole measurement problem, and I don't know, like, the multi-universe, like, etc. It's a very nice story. Like, it's I think it is one of the most fascinating topics for Hollywood to make, God knows how many different movies out of like, multiverse, etc. But at the end of the day, like, there is a problem. How to tackle that? Still, we are struggling. It's, as you mentioned, observer theory. Like, I think this is one of the things that quantum theory does not provide any answer. Maybe alternatives such as like, Wolfram Physics Project provide some insight on how to tackle that problem. But if I may, last, comment from my side on foundation of quantum. If you ask my opinion, like, since I work on the foundation for a while, I believe quantum theory is like statistical limit of a more fundamental theory. So like, it's the connection of quantum with the more fundamental theory is very similar to the connection of thermodynamic with the statistical mechanic. So like, that's how, like, that's how, they are connected. And if we take that analogy seriously, you can never ever go to a statistical mechanic starting from thermodynamic. Like, think about the concept of heat, the concept of, I don't know, entropy, or like everything that we have in thermodynamic. It doesn't tell you anything about the statistical mechanic. It's like a statistical mechanic is completely like a different thing. Like, you know, you have classical mechanic and then a statistical, like, you know, on the top of that. And then you manage to drive a big portion of, like, you know, thermodynamic. I feel, you know, quantum is the same. Like, you know, what's going to be the more fundamental theory? I think its concepts, its fundamental ideas is going to be so different from quantum that initially we would see lots of pushback from scientists that, no way, like, you know, it shouldn't work. And I think that was a story of, you know, statistical mechanic, Boltzmann, Maxwell, everything that they did. Like, you know, that's the same story.
So interesting. Okay, can we take a couple more questions? Then we can close the stream for the week. Okay, so we said here, if you measure a particle, don't you perturb the structure with energy and measure that energy back? I think it is important to track that energy. So that's just a comment, I guess.
Depends so important on what, for what. Usually it is ignored essentially when you do the measurement. It's all the information together with the energy may be leaking into environment. That's what measurement means. You just decohere your state into some other state, which leaves some information absent.
Like in quantum computing, you're always trying to maintain the state. It's like very difficult. And then whenever you're making a measurement, or someone's explained to me, like when you're moving lasers around, sometimes there's even Doppler effects that you have to take into consideration just because of the movement. So you're trying to cancel all of that out to maintain the state, right?
Yeah. It's more, I think it's more about maintaining entanglement rather than a single state. It's even much harder.
It's very hard.
Yeah.
Check out Fermi's golden rule. Another comment there. And then Perpetual Side says, I would love to see this for several qubits, which we did comment on earlier. And again, there's a weird amount of hostility around this stuff, which is weird. Okay, let's see if there's any questions. They just said we appreciate the conversation. And
I want to put a link in the chat here, James. If you want, you can share with
for sure.
our audience.
Is this the Wigner's friend essay?
No, this is basically like, you know, the very last talk given by John Stuart Bell. Like, you know, it's his talk at Trieste, the International Center for Theoretical Physics. That was his very last talk before his sudden death. And many leading figures like, you know, Dirac, like all the, like, you know, who were alive at that time, you know, the founding father of quantum theory, they were present in that talk. So it's a very good summary of, like, you know, what's going on, you know, the question that, you know, our audience asked, what happens during the measurement? And, like, you know, there are many open problems. Like we, for example, in quantum computing, we just represent measurement by bucks, and you would say, okay, this is what it happens. But really, like, if you just become very picky, like when we can say a measurement is happening, we don't know. Like, you know, it's a like classical to quantum. Where is that boundary that suddenly a collapse? We don't know. And it's an active field of research, and many scientists are seriously pursuing to see, like, you know, if there is any fingerprint of, like, you know, some non-linearity beyond, like, you know, quantum theory.
Do you think observer theory can fit in here to help with this? And how would you describe the promise of observer theory at the moment? What's your take on it?
I think Nick should comment on that. Like, you know, he has much more intellectual experience on observer theory.
Well, I'm not sure. I'm still confused about how you would fit observer, whether you actually want to do it. Even like in the Bohmian mechanics we discussed today, it's supposed to get rid of any presence on an observer and have the actual definite properties of the reality, right? So from this perspective, you don't have to introduce an observer, but from other perspective, because there's still, in the quantum case, as I showed, that it should depend on your measurement setup, because that would actually determine which basis you're measuring and what would be the outcomes be. So you can't really describe it with an actual single property. So there are either some multiple properties, so it depends on the actual observer.
Yeah, I mean, like the experiment itself could be a type of observer, I guess, in that case, right? It's an interaction, maybe.
Yeah, that's final interaction of the system. I don't know. It's any explicit introduction on observer, I think it's usually unnecessary. It just means it means just you have to create another theory that has an observer as another system.
Yeah.
So
there is this very famous, quote by John Stuart Bell. Let me just read it. The quote. What exactly qualifies some subsystems to play the role of measurer? Was the word wave function waiting to jump for thousands of millions of years until a single cell living creature appeared? Or did it have to wait a little longer for some more highly qualified measure with a PhD? So that's basically his way of saying that the emphasis on this is basically the measurement problem. It's how to tackle that. Honestly, I don't know. And but as a scientist, I belong to that school of thought that at the end of the day, whatever, we have to test them experimentally. I love that very famous example of field quantization and the Lamb shift. Scientists, they were not confident that if quantization is the right scenario. And Lamb, he did the experiment that the Lamb shift in the hydrogen atom, it was observed, and that was basically the kind of the fingerprint of okay, quantization is a good approach. Let's do that. So I think at the end of the day, any of these ideas, once we have a way to falsify, to test that's the scientific way. This is science 101. Science is based on observation. So that's how we should test our assumptions.
I like that phrasing there. It's like taking the measurement problem seriously. That could be one way of describing the benefit that observer theory development could help with quantum mechanics, maybe. I like that. Okay, thanks everyone for the stream, and hope you enjoy your weekend. And some nice quantum thoughts to ponder for the weekend before we kick off next week again. Thanks everyone.
Thank you guys.
Okay.